So we're continuing to get a more and more detailed and correct picture of bonding in covalent molecules. We predicted bond angles using a very simple VSEPR theory. Now what we're going to do is relate that to what we know about atomic structure and atomic orbitals. So what we have to remember in this section on valence bond theory is that a covalent bond is just a shared pair of electrons. And where do we find electrons? Electrons live in orbitals. So what that means is in order to be sharing the electrons, the orbitals for two different atoms must overlap to make the bond. So I'm going to draw some pictures showing the orbitals overlapping to make these particular molecules. And let me say, for some of you, this will be the first completely new thing that I've done all semester. So don't panic. I'm going to show you how to deal with it one thing at a time. And this first time, you won't see this coming, probably. Now, I love this unit of drawing molecules in the course. You remember that in order to predict the shape using VSEPR, I had to draw the Lewis structure first. In order to show the orbitals overlapping, I need to see the correct shape with VSEPR, which means I have to draw the Lewis structure first. So let me start that routine up here with methane, CH4. And just a recap of what we've seen before. The Lewis structure has the 4 hydrogens around the carbon. We saw that that had 4 electron pair domains around the central atom, and we knew that that had tetrahedral electron pair geometry. So I'm drawing a nice little tetrahedron there. I'm afraid that I memorized that the tetrahedral angle was 109 degrees. I want to account for that 109 degree angle by looking at the atomic orbitals for that carbon at the center. So let's see, I had to make a tetrahedron that was based on 4 electron pair domains that made 4 equivalent bonds. Now I'm going to draw a picture of the orbitals on an isolated carbon atom and see how that fits in. The valence orbitals for carbon are at the second energy level. I'm not going to draw the 1s orbital. It's a core orbital. We're only going to worry about the valence electrons here. So at the second energy level, we had 1 s orbital, there's the 2s, and 3 2p orbitals. There's the 2px, the 2py, and the 2pz. That's what it looks like, but I can also represent the relative energies of those orbitals. The 2s was lower in energy than the 3 2p's. When we looked at the periodic table, we could see that carbon has 4 valence electrons. 1, 2, 3, 4. So does it look like carbon wants to make 4 equivalent bonds? Well, no, I've got a problem there. First of all, it looks like I would only make 2 bonds if I shared electrons, or maybe I could make 3 bonds if I provided a pair from another atom, but I don't see 4. The bigger problem in this game that I'm playing is that the angle between the p orbitals is 90 degrees. P orbitals are at right angles to each other. So this isolated carbon atom does not explain the bond angle we see in a methane. It's 109 degrees and not, it's 90 degrees and not 109. So I'm going to have to do what they call a hybridization of those atomic orbitals. You biologists know that when I hybridize something, if I make a hybrid plant, I blend the properties of the parents. That's the same thing I'm going to do here. I'm going to blend the 4 valence orbitals, the 1s and the 3 2p's, and I'm going to break them into 4 equal pieces because I know I want to make 4 equivalent bonds in methane. So here's the energy. I'm going to break them into 4 equivalent orbitals. I blended 4 orbitals and I get 4 orbitals. That's one of the rules of this game. The energy of these new orbitals I drew is intermediate between the energies of the s and the p. It's kind of a weighted average. And since I blended 3 p orbitals and only 1 s, the energy of these new orbitals is 3/4 of the way up, closer to the 2p than the 2s. Now, if I want to distribute the 4 valence electrons there, 1, 2, 3, 4, Hund's rule says we half fill the sublevel before we pair it. Hey, look at that. That makes 4 orbitals that want to get another electron, to share electrons to make 4 equivalent covalent bonds. Now, what do we call these orbitals? We name them based on how we made them. I wanted to get 4 equivalent bonds. I wanted to get 4 equivalent hybrid orbitals. So I blended 4 unhybridized orbitals. I made the new ones from an s and 3 p's, so this is called the set of sp3 orbitals. Each one of them is an sp3 hybrid orbital. Now, the fun part, what does it look like? Here's my carbon. I'm going to draw an sp3 orbital. And it's got a great big fat front lobe and a little tiny back lobe. Hybrid orbitals always look like that. That's probably the last time I will draw the little tiny back lobe. That just clutters up my picture. What's special about sp3 hybrid orbitals is the angle that they're arranged at. sp3 orbitals are arranged at the corners of a tetrahedron. Coincidence? I think not. This hybridization game is just a game that I play to explain the observed bond angles. So it's not a coincidence that these sp3 hybrids are in a tetrahedral arrangement with a 109-degree angle between them. Now, I haven't yet answered the question. I haven't drawn the orbital overlap that leads to bond formation. I've still just got atomic orbitals. I haven't put it together to make a molecule. These are atomic orbitals. These are still atomic orbitals, but they're called hybrid atomic orbitals. So to truly answer the question, let's go on and have the orbitals for the carbon overlap with the hydrogen. Before I do, though, I am not the world's greatest artist. So I'm just going to slip in the picture from your textbook. Fortunately, they are good artists. They've got the 4 orbitals on different axes. I don't know why they don't have them overlapping like I did. They just don't. And then they've got the set of 4 sp3 hybridized orbitals. Remember, I showed one pointing straight up, one pointing, and the other one's at 109 degrees to that. So that made tetrahedral arrangements of sp3 hybrid orbitals. All right, let's stick the hydrogens on. So to really answer the question, for methane, I'm going to put together the hybridized building blocks like I'm putting Lego bricks together. I drew an sp3 hybridized carbon. sp3 orbitals come in sets of 4, and they're arranged at the tetrahedral angle. This is just the sp3 hybridized building block I showed on an earlier slide. Now, the orbitals have to overlap with the orbitals for a hydrogen to be shared between them to make a covalent bond. And what valence orbital does the hydrogen use? Well, the valence orbital for hydrogen is the 1s. So I'm going to stick the 1s for a hydrogen end on at the end of each of the carbon sp3s. And every time I let them overlap, I get a region here where the probability of finding an electron is greater where those two orbitals overlap. For you calculus and theoretical physicists in the house, what I'm saying is that the wave equation for the hydrogen orbital and the wave equation for the carbon sp3 orbital have constructive interference there. Not to worry about that. Now I've just made a covalent bond, and there's more than one type. I just made a sigma bond. That's the Greek letter sigma, and the only reason we use Greek letters is there are not enough English ones. This particular sigma I made by overlapping the 1s from the hydrogen with the sp3 from the carbon. What makes it a sigma bond is that I overlap them end to end. So I'll jot down a few points about sigma bonds. They are formed by the end-to-end overlap of atomic orbitals. Another thing I notice about them is that the probability of finding an electron is greatest where those orbitals overlap. So that means that the probability of finding the electron in the covalent bond, the shared pair, is greatest between the two nuclei. The electron density is greatest along the internuclear axis. Now, you may not be able to imagine any other way to do it at this point, but I will show you another way when we get to a different molecule. One other criterion that makes it a sigma bond is that we say it is cylindrically symmetrical. What that means is that if I rotated around this bond, and I'll show you that with my model kit, it would look exactly the same all the way around. In other words, if I cut the bond open as a cross section and look down it, it would look like a circle in cross section. And again, I'll show you that with my molecular models. So I wanted to illustrate what I was telling you about the orbital overlap in methane with my model. When I draw the cartoons of the hybrid orbitals on the page, the orbitals are fat and take up a lot of space. This model kit is going to underdo it with its sticks instead of fat lobes. But I can see the tetrahedral geometry here for methane. And what I can see is the formation of a sigma bond when the hydrogen 1s overlaps with the sp3 on the carbon. I told you that this was a cylindrically symmetrical orbital, the sigma orbital, because when I turn around the top, it looks the same all the way around. The other thing I told you is that if I cut this bond in cross section and opened up the two halves, then it would look like a circle in cross section. All right, that's the story for methane. Now, let's try that again with ammonia. To know what kind of hybrid orbitals to use for my building block, I have to know the shape. This hybridization game is just a game to explain the shape of the molecules. To know the shape, through VSEPR theory, I need to draw the Lewis structure. So let's start that game up. And hopefully, having seen the last example, you're going to anticipate this a little bit better. All right, there's my Lewis structure for ammonia. Based on the Lewis structure, I can see 4 electron pair domains around that central atom. 4 electron pair domains means I have a tetrahedral electron pair geometry. But because I have a lone pair, one corner of the tetrahedron is missing. Although my electron pair geometry is tetrahedral, my molecular geometry is trigonal pyramidal. It's the electron pair geometry that tells me the hybridization. If I have 4 electron pairs, that gives me a tetrahedral geometry. And that is exactly equivalent to saying that I have sp3 hybridization. The tetrahedral electron pair geometry, electron pair geometry, is responsible for a bond angle close to 109 degrees. Yeah, the lone pair squishes it down a little bit, but it's roughly 109 degrees. And we saw with the previous methane example, if I want bond angles of 109 degrees, I use sp3 hybridization. Now, if I explained that slowly to you, let me give you a shortcut. If I have 4 electron pair domains, then what kind of hybridization do I need? And S and 3 P's is 4. Adds up to 4 electron pair domains, tetrahedral. Now, I'm not going to draw a picture of the orbitals again, but I can show the energies. On the left here, I'm showing the atomic orbitals for an isolated nitrogen. But if I had 1, 2, 3, 4, 5 electrons, that looks like it wants to make 3 bonds, but the angle between the P's would be 90 degrees. And that's not what VSEPR predicts. That's not what's experimentally observed. So, why do I have to play the hybridization game? Because my unhybridized orbitals don't explain the shape. We want 4 electron pair domains. We want 4 equivalent hybrid orbitals. We're going to blend them and get the 4 sp3 hybrids. Now, where do the 5 valence electrons go? 1, 2, 3, 4, 5. And now it looks like I'm going to make 3 bonds by sharing those 3 electrons. And the angle between those bonds is 109 degrees. Now, all this is background thinking. The question part of the question, if you look back a couple of slides, is to draw the molecule showing the orbitals overlapping. So let's really answer the question. So for ammonia, let's put together our hybrid building blocks. That ammonia is sp3 hybridized. sp3s come in sets of 4. At the corners of a tetrahedron. Coincidence? I think not. That's why we're playing this game. So now I'm ready to start overlapping the sp3 hybrid orbitals for the nitrogen with the valence orbitals for the hydrogen, which are the 1s. I'm going to make 1 sigma bond by overlapping a hydrogen 1s here, and another one over here, and another one over here. But remember, I had a lone pair as well. The 4th sp3 has the lone pair in it. And not by coincidence, I hope if you look at those nuclei, that it looks like it's a trigonal pyramidal geometry. All right, let's call that good for part 1. When we come back to part 2, we'll look at other geometries that require different types of hybrid orbitals.